McNair, and this is my lab report for Faraday's Law, Lab 4. So to start, the purpose of this lab was to collect observational data of a magnet falling through a tube of aluminum foil and record the observed time that it took for it to fall through the tube. And we repeated this 6 times and took the average time to get 0.298 seconds. And then we modeled the magnet tube interaction computationally through GlowScript, which resulted in a prediction of 0.341 seconds. So as we can see, the prediction is that it would take longer than what my observed value was. So let's get into it. So key physical principles. First, magnetic flux is the integral of the magnetic field dot in hat dA. And when it's perpendicular, then it's just the magnitude of the two multiplied together. This equation right here is for the magnetic force on a dipole, which is important for the computational model because the bar magnet is essentially a dipole. And then Faraday's law and Lenz's law go hand in hand. Magnetic force, and also we need to know, I didn't mention this in here, but Newton's second law, the net force is equal to mass times acceleration, and also gravitational force is mass times gravity. And then we need to know that the emph is the negative change in flux, and then current is emph over R from Ohm's law. So some background, initial conditions, system is the bar magnet, surroundings is the foil, earth, etc. And then here I just have some dimensions of the tube, the mass of the magnet that I used. We're starting at time is t equals 0, and then velocity is v is equal to 0 meters per second. And then the magnetic dipole moment of the magnet is 3.985 amp meter squared, which is my value that I got from lab 2. And then we're also assuming that the bar magnet is the only object producing a magnetic field in the area, and that air resistance is negligible. So from my observed model, this is just the procedure over here, and then these were my recorded times for each trial, and then my average was 0.298, as I mentioned before, seconds. So then in the computational model, here we just kind of are initializing, and then I used my code from before to create the magnetic field of the bar magnet, and then here is the function for calculating the flux, and then some simulation thingies, more code, and then here's my final velocity versus time graph, and as you can see here, my time was 0.341 seconds. Some sources of error: there might not have been enough foil on the roll of aluminum foil. My roll was already used, so it wasn't like super thick, so it may, like, my time may have been really short compared to like what would be expected, which we actually kind of see that in the predicted results from the computational model versus my results. Also, other external magnetic fields may have been present. I had some electronic devices in the room, so may have been something with that, I don't know. Inaccurate measurements of the dimensions of the tube. I used a ruler to measure, but you know, there's always like sig figs and all that, so. And then not entirely accurate time measurements from video analysis. I tried to scrub through the videos as best as I could to get like the exact moment, but you know, sometimes there's like a little bit of a like, it's hard to get it exactly is what I'm trying to say. So for the what if discussion notes, the first question is, what if the resistivity of the conductor were reduced as close as possible to 0? The magnet would fall a lot more slowly due to a larger induced current and consequently a larger magnetic force on the magnet. And then if holes or slots were cut into the tube, the magnet would fall quicker because the slots and holes would mean that there is less aluminum foil present, and there will be a smaller induced current and smaller magnetic force acting on the magnet. Thank you.